Imagine a star, much like our own Sun, but 1,470 light-years away. It should be shining steadily, predictably, like a cosmic lighthouse. But this star doesn't. It flickers. It dims. Not in the regular, predictable way of a planet passing in front, but erratically, dramatically, sometimes losing up to 22% of its brightness. That's like a fifth of the star just vanishing. And then, just as mysteriously, it brightens again. This isn't a hypothetical scenario, a thought experiment, or a science fiction story. This is real. This is KIC 846-2852, better known as Tabby's star, or Boyajian's star, and it's one of the most profound and perplexing mysteries in modern astronomy. What could possibly cause such bizarre behavior in a seemingly ordinary star? This isn't your typical astronomy story. We're not talking about planets orbiting distant stars, or beautiful nebulae, or even supernovas. We're talking about a star that behaves like no other star we've ever seen. Tabby's star, officially designated KIC 846-2852, is an F-type main-sequence star, a bit hotter and more massive than our Sun, located in the constellation Cygnus. And it's doing something deeply weird. This video will delve into the unprecedented observations, the scientific head-scratching, the discarded hypotheses, and the lingering mystery of Tabby's star. Is it a natural phenomenon we simply haven't encountered before? A sign of incredibly rare cosmic events? Or could it be something far more significant? Let's examine the evidence. 1. The Kepler discovery and the WTF star. The story of Tabby's star begins with NASA's Kepler Space Telescope, a mission specifically designed to find exoplanets. Kepler, launched in 2009, spent years staring at a small patch of the sky, meticulously monitoring the brightness of over 150,000 stars. The principle is simple. If a planet passes directly between its star and us, a transit, it blocks a tiny fraction of the star's light, causing a slight, temporary dip in the star's brightness. These dips are usually tiny, often less than 1%, and they're periodic, repeating with the planet's orbital period. In 2011, citizen scientists participating in the Planet Hunters Project, a program that allows volunteers to analyze Kepler data, flagged something highly unusual about the star KIC 846-2852. The star's light curve, a graph plotting its brightness over time, showed dips that were unlike anything seen before. They weren't the small, regular, symmetrical dips of a transiting planet. These dips were huge, irregular, asymmetric, and aperiodic. In some cases, the star's light dimmed by as much as 22%. That's an enormous amount of light to be blocked, far more than even a giant planet like Jupiter could account for. And the dips didn't follow any predictable pattern. They occurred at seemingly random intervals, sometimes lasting for just a few days, sometimes for weeks. The lead scientist on the professional analysis of this star was Tabitha Boyajian, an astronomer at Yale University, now at Louisiana State University, hence the star's nickname, Tabby's star. It's also sometimes called Boyajian's star or, more informally, the WTF star, where WTF initially stood for Where's the Flux? A reference to the missing starlight, though the more common, colorful interpretation of WTF certainly applies. Boyajian and her colleagues published a paper in 2015, titled Where's the Flux? Outlining the unusual observations and exploring various possible explanations. The paper itself acknowledged the strangeness of the data, stating that no known or proposed stellar phenomena can fully explain all aspects of the observed light curve. This was a scientific understatement of epic proportions. They had stumbled upon a genuine astronomical mystery. 2. Natural explanations and their shortcomings. The scientific method dictates that we start with the most likely explanations, the ones that involve known phenomena, before we jump to more exotic possibilities. So, what natural processes could potentially cause such dramatic and irregular dimming events around a star? Several hypotheses were proposed and investigated. One of the first ideas was a swarm of comets, or perhaps the fragments of a recently disrupted planet, passing in front of the star. A large cloud of dust and debris, unevenly distributed, could potentially block a significant amount of light, and the irregular shape of the cloud could explain the asymmetry of the dips. However, this explanation quickly ran into problems. Comets and planetary debris, when heated by a star, would be expected to emit a significant amount of infrared radiation, a heat signature that should be detectable by telescopes. But observations of Tabby's star showed no excess infrared radiation, ruling out a large, dusty cloud close to the star. Another possibility was that the star was surrounded by a large, irregular dust cloud, perhaps the remnants of a protoplanetary disk, the disk of gas and dust from which planets form. However, Tabby's star is an F-type main sequence star, meaning it's a mature star, well past the stage where it should have a protoplanetary disk. Furthermore, a dust cloud, even an irregular one, would be expected to cause a more gradual dimming and brightening, not the sharp, sudden dips observed in Tabby's star's light curve. And again, the lack of excess infrared radiation posed a problem for this explanation. Some researchers proposed that the dimming could be caused by intrinsic variations in the star itself, perhaps some kind of unusual stellar activity, pulsations, or flares. However, F-type main sequence stars, like our Sun, are generally very stable and don't exhibit the kind of dramatic and irregular brightness variation seen in Tabby's star. While stars can have star spots, darker, cooler regions on their surface, the scale of the dimming would require a star spot far larger than any ever observed, covering a significant fraction of the star's surface, which is highly improbable. Another idea involved a large planet with a system of rings, or a planet with a swarm of Trojan asteroids that share a planet's orbit. But these scenarios would produce more regular and predictable dimming events, not the erratic and asymmetric dips seen in Tabby's star's light curve. Furthermore, a planet or a ring system large enough to block 22% of the star's light would be easily detectable by other means, such as radial velocity measurements, which measure the wobble of a star caused by the gravitational pull of orbiting objects, and no such planet has been found. 3. The alien megastructure hypothesis, a bold idea. With the most common natural explanations failing to fully account for the bizarre behavior of Tabby's star, the scientific community, and certainly the public, began to consider more unconventional ideas. And that's where the alien megastructure hypothesis, arguably the most attention-grabbing explanation, entered the picture. This idea, while seemingly ripped from the pages of science fiction, is not entirely without a scientific basis, at least in the realm of theoretical possibilities. The core concept revolves around the idea of a Dyson sphere, or, more accurately in this case, a Dyson swarm. This concept was first proposed by physicist Freeman Dyson in 1960. Dyson reasoned that as civilizations advance and their energy needs increase, they might eventually seek to harness the entire energy output of their star. One way to do this, he speculated, would be to build a massive structure, or a collection of structures, that would completely enclose the star, capturing all of its radiated energy. A complete Dyson sphere would be a solid shell, but a Dyson swarm would consist of a large number of individual structures, solar collectors, habitats, or other components, orbiting the star in a dense formation. The alien megastructure hypothesis for Tabby's star suggests that the observed dimming events could be caused by a partially completed or irregularly shaped Dyson swarm passing in front of the star, from our perspective. The large, asymmetric dips in brightness could be caused by large clusters of these structures, while the more frequent, smaller dips could be caused by individual components or smaller groups. The lack of a repeating pattern could be explained by the complex orbital dynamics of a large number of objects orbiting the star at different distances and inclinations. The idea of an alien megastructure around Tabby's star gained significant traction when astronomer Jason Wright, then at Penn State University, suggested that the unusual light curve was consistent with what you might expect from an alien civilization building such a structure. This, of course, generated a huge amount of media attention and public excitement. The Search for Extraterrestrial Intelligence (SETI) Institute even pointed radio telescopes at Tabby's star, looking for any signs of artificial radio signals that might be associated with an advanced civilization. However, no such signals were detected. It's crucial to emphasize that the alien megastructure hypothesis is highly speculative, and remains a very long shot. There's no direct evidence to support it, and many scientists remain highly skeptical. The lack of excess infrared radiation, which would be expected from a large structure absorbing and re-emitting the star's energy, is a major problem for this hypothesis. However, the sheer weirdness of Tabby's star, and the difficulty in finding a completely satisfactory natural explanation, has kept the alien megastructure idea alive in the public imagination, and it continues to be discussed and debated, even among scientists. 4. The dust cloud, a more likely culprit? While the alien megastructure hypothesis grabbed headlines, the scientific community continued to search for more plausible, natural explanations for Tabby's star's unusual behavior. And in recent years, a new leading theory has emerged: dust. But not just any dust, a very specific, and very unusual, kind of dust cloud. One of the key breakthroughs came from analyzing the color of the light during the dimming events. If the dimming were caused by large, solid objects, like planets or components of a Dyson swarm, they would block all wavelengths of light equally, causing a gray dimming. However, observations showed that the dimming was stronger at blue wavelengths than at red wavelengths. This color dependence is a strong indication that the dimming is caused by dust, as fine dust particles scatter blue light more effectively than red light. This is the same reason why the sky is blue and sunsets are red on Earth. So, the current leading theory is that Tabby's star is surrounded by a cloud of dust, but this is no ordinary dust cloud. It has to be very unusual to explain all the observed characteristics. It can't be a uniform, symmetrical ring, like the rings around Saturn, because that would cause regular, predictable dips. It has to be highly irregular, clumpy, and perhaps elongated, to account for the asymmetric and aperiodic dimming events. And it has to be relatively transparent at infrared wavelengths, to explain the lack of excess infrared radiation. One model that seems to fit the data is a cloud of dust orbiting the star in a highly eccentric, elongated orbit, perhaps produced by the disintegration of a large exocomet or a family of exocomets. As these comets approach the star, they would be heated and release large amounts of dust and gas, creating a temporary, uneven cloud that could block some of the star's light. Another possibility is that the dust is orbiting in a ring, but the ring is warped or tilted with respect to the star's rotation, or that it contains large clumps or gaps that cause the irregular dimming. While the dust cloud theory is currently the most favored explanation among astronomers, it's not a perfect solution. There are still many unanswered questions. What caused the dust cloud to have such an unusual shape and composition? What is the origin of the exocomets, if that's the explanation? And why haven't we seen similar dimming events around other stars? Tabby's star remains an outlier, a unique and challenging object that continues to test our understanding of stellar and planetary systems. 5. The enduring mystery and future observations. So, where does this leave us? Is the mystery of Tabby's star solved? Not entirely. While the unusual dust cloud explanation is currently the most favored by the scientific community, it's not a definitive answer. There are still many unanswered questions, and the possibility of something even stranger going on can't be completely ruled out. Tabby's star remains an object of intense scientific interest, and astronomers continue to monitor it using a variety of telescopes and instruments. Future observations, particularly at different wavelengths of light, could help to further constrain the properties of the dust cloud, determine its composition, and perhaps even reveal its origin. More detailed observations of the star itself could also reveal subtle variations in its brightness or activity that might be related to the dimming events. And the search for similar objects around other stars is crucial. If we can find other stars that exhibit similar behavior, it would suggest that this is a more common phenomenon than we currently realize, and it might help us to develop a more general understanding of the processes involved. The story of Tabby's star is a perfect example of how science works. It starts with an unexpected observation, a puzzle that doesn't fit our existing models. Scientists propose different hypotheses, test them against the available evidence, and refine their theories as new data comes in. Sometimes, the answer is relatively simple and mundane. Other times, the mystery deepens, forcing us to reconsider our assumptions and to explore new possibilities. And even when a likely explanation is found, there are often lingering questions and uncertainties that keep the investigation going. The universe is vast and complex, and there will always be more to learn. So, after this deep dive into the heart of the Tabby star enigma, the unprecedented dimming events, the discarded hypotheses, the lingering dust cloud theory, and the still present possibility of something even more extraordinary, what's your take? Is this a natural phenomenon, albeit a rare and unusual one? Is it a sign of something we've never seen before, something that challenges our understanding of stars and planetary systems? Or could it still, despite the odds, be a hint of something truly alien? The beauty, and sometimes the frustration, of science is that it doesn't always provide easy answers. But it does encourage us to keep asking questions, to keep exploring, and to keep pushing the boundaries of our knowledge. What do you think is the most likely explanation for Tabby star's weird behavior? Do you have any alternative theories? And what other cosmic mysteries are you most fascinated by? Share your thoughts, your speculations, and your questions in the comments below. Let's have a respectful, open-minded, and intellectually stimulating discussion about this incredible enigma. And if you enjoyed this journey into the unknown, please subscribe to the channel. We've got plenty more mysteries of the universe to explore. Hit that notification bell so you don't miss a single video. Give this one a thumbs up to show your support, and share it with your friends who are fascinated by space, science, and the unexplained. Until next time, stay curious, keep looking up, and remember, the universe is full of surprises, and we're only just beginning to uncover its secrets.